Yeah, I'm going to be talking about, I'll try to give a survey-ish like talk about work that's in a, by now, long series of papers with Mihalis Yannakakis, but after an initial setup to kind of give you the complexity landscape within which the problems I'm interested in reside, I'll shift to talking about somewhat more recent work, which is joint work with Mihalis and with a seriously sharp PhD student, Alistair Stewart, who's been helping us solve some of the open problems that were in the area that I'll be talking about. So, okay, so let me start setting the context. So, here's a classic fixed point theorem that I know many of you in the audience know this very well, but I don't know if the PhD students in the back row may be familiar with these things, but okay. So Brouwer's fixed point theorem tells us, this classic fixed point theorem that says every continuous function from a compact convex subset of Euclidean space, D, to itself, must have a fixed point. There must be a point that gets mapped to itself. And, it's not difficult, when you try to reason about this, it's not difficult to see that there's some magic here. It's the fact that there always exists a fixed point is not at all a trivial fact. And you can even do simple thought experiments about it, like, take two sheets of paper, crumple one of them on top of the other, and it must be the case that there exists a point in the crumpled sheet that has exactly the same coordinates as the point that is directly sitting on top of. And that's a consequence of Brouwer's fixed point theorem, irrespective of where you place the crumpled sheet. And it's actually mind-boggling to think why that must be the case, but it is. So anyway, so there's this classic fixed point theorem, and it turns out that many computational tasks that we are interested in, coming from many, many different domains, can often be boiled down to the problem of computing or approximating a fixed point. So we're somehow given a Brouwer function, a function that is a continuous function from a compact convex set to itself, and we want to compute, or in many cases, we can't really hope to compute because, for example, all of the fixed points may have irrational coordinates. So when we say compute, what we mean is some kind of approximation. So we want to approximate a fixed point typically. And there are two different notions of what we might mean by approximating a fixed point. And these two different notions turn out to have rather different computational complexity implications. So what are these two standard notions that one can consider as notions of approximating a fixed point? Well, we'll call them almost approximation and near approximation. So in almost approximation, we're given this function, and we want to compute a rational vector where such that this rational vector is almost fixed by the function, by which we mean that the distance between the point that x prime is mapped to and itself is less than epsilon. And here, for concreteness, I'm using the L infinity norm, but in general, you can consider any other norm if you felt like it. It doesn't matter. The norm is not particularly relevant here. I'm just trying to make it concrete, okay? Now, we can also consider near approximation. But by the way, I'm getting some kind of echo feedback in my, let me just try to move this. Yeah, okay. I hope the recording can still catch it. Okay, so we can also consider near approximation of a fixed point. So what do we mean by that? For near approximation, we mean we want to compute a rational vector where there exists an actual fixed point. Now remember, the actual fixed point may have irrational coordinates for all we know, some whatever. But what we want to make sure is we are close to an actual fixed point, a point that is mapped exactly to itself. Okay? And these two notions turn out to have rather different complexity implications. If you don't have a kind of computational complexity mindset, you might think to yourself, well, wait a second, in the limit, these two notions are exactly the same thing, right? And that is true indeed, in the limit they are, but it's not the case that from a computational point of view, in other words, given epsilon, computing an almost fixed point has rather different complexity characteristics than trying to compute a near approximate fixed point. And the kinds of problems that I will focus on later in the talk are the kinds of problems where the only approximation that makes sense, that matters to us, are near approximation, and that's what we want to do. In particular, for example, there are certain stochastic processes that I will talk about later where the event, the probability of a certain event is captured by the unique Brouwer fixed point of some function, and I want to compute that probability. That's all I'm interested in. I'm not interested in the function that if there are almost fixed points that are far away from that unique probability that I'm trying to compute, I'm not particularly interested in them. So we're going to be focusing on this notion of near approximation. Okay? Okay. So and I will, but I will elaborate on the complexity implications in both of these settings. And what I wanted to jump right into right away is I want to define a complexity class based on what I've just told you. Namely, I'm actually going to define two complexity classes. So this is in some sense a model. What I've done is I've merged the definition of two complexity classes. One is a real valued class where it's not residing in the standard models of computation that we might think about, because it's about, it sort of speak, if you want to think about it, you can think about it in terms of like Blum-Shoup-Smale type models, but fixed P is a class of real valued total search problems, and fixed P sub A, the approximate version of fixed P, is a class of discrete total search problems. And what are they? So the input to the class is we're going to be presented somehow with a Brouwer function, a function that maps in particular, in this case, the compact convex domain is the unit n cube, and it's going to map the unit n cube to itself, and the function is given to us by nothing other than an algebraic circuit or a straight line program that uses gates plus, times, and max, and as well as rational constants, both positive and negative rational constants. And it has n input variables, x1 through xn, and it also has n output gates. And such a circuit, in a natural, obvious way, defines a continuous function. Well, it defines a continuous function, and you might ask yourself, well, how do I know it defines the unit n cubed to itself? You can actually syntactically impose that using max and min. And we can define min in terms of max. You can say, you can always impose the fact that it's going to map the unit n cubed to itself. Okay? So this is our input. And in the case of fixed PA, in the approximate setting, we are additionally given an error parameter, epsilon greater than 0, as input. Now, what do we want to do? For output, in the fixed P setting, we actually want to compute the actual fixed point, which makes no sense in the Turing model in general, because the actual fixed points may be irrational real values where, what do we mean exactly by computing them? But in the approximate version, all we want to do is compute an epsilon near approximation of an actual fixed point. So we want to get epsilon close to an actual fixed point, okay? And if we close these problems under suitable polynomial time suitable reductions, so let me be a little bit more specific about that. In the case of fixed P, we have to be a little bit careful because this is a real valued search problem. So what kinds of reductions are we talking about? I start with some real valued search problem. Now, my reduction is going to have the following property. I'm going to, in polynomial time, compute a instance of fixed P, right? Now, for any fixed point of that function, there will be a separable linear map with rational coefficients that will map back to an answer to my original problem, okay? And so this in a sense, both combines a polynomial time search problem reduction and a reduction that works also in the real valued model. And so these, under these kinds of reductions, we'll call the resulting class fix P and this approximate version fix PA. So I know this is a mouthful, so if somebody has not understood it, particularly the people in the back rows who are the students here, a lot of others in the audience, particularly those who have come from the UK, will have seen this stuff in various forms. So it would be great if you feel confused by anything I say to just stop me and make me explain things better. Go ahead. Okay, so the notion of reduction is as follows. So these are total search problems, right? So what is a total search problem? It's not a yes/no answer that we're looking for. We're looking for there's a bunch of solutions to a problem, and we want one of those solutions. The problem here is that for fix P, not for fix PA. Fix PA is a discrete total search problem, and I just need to compute one of those answers, right? But for fix P, the answer itself is a vector of real values. What do we mean by kind of a reduction that works in that setting? What we mean is as follows. I start with my input, which is a string, right? I transform it to another string, namely a string that describes such an algebraic circuit, right? So that's one direction. And then I obtain an answer to this real valued search problem, namely a vector which is a fixed point, let's say. And then I map back that answer to an answer to my original problem from which I reduced using a so-called separable linear map. What do I mean by that? That means that it just coordinate-wise picks out particular coordinate. It's almost like a projection. It's not quite a projection. It's just taking particular coordinates of the answer and multiplying them by, let's say, a polynomial-sized integer, and maybe adding to it something else, okay? And then that's my answer to the original problem. In fact, a little bit more flexibly, I allow multiplying by a polynomial-sized rational number and adding a rational number, okay? So that's the full description of, so it's what we call so-called separable linear reductions in the fixed P paper that associates with this, but never mind, okay?
How about the complexity of polynomial?
You mean the standard reduction?
Well, no, I mean the fixed P. So separable linear map, what are complexity constraints?
Well, in the separable linear, the rational numbers, the coefficients are polynomial sized. That's it. So it's both, in some sense, if you think about it, it's both a polynomial time reduction, search problem reduction in the standard sense, and at the same time, it's also a, if you like, nice reduction in the real valued model. Okay?
There's nothing uniformity condition. I mean, there's many such concepts. So you need to be able to reduce time efficiently.
Yeah, no, these are polynomial time computable numbers that are, everything is polynomial time computable from, so that's what it means to be, so everything, all the parameters of the reduction are polynomial time computable from the string that's your input, okay? Okay, are we good? Everybody okay? Okay, good. So you might not think that this is a particularly robust class. It might seem to you that it's a little bit ad hoc or something like that. But trust me, it's very robust. So you can add all kinds of other operators to this class, and it won't change the class. You can change the domain to, for example, any convex polytope, and it won't change the class. You can even change the domain to ellipsoids suitably defined, arbitrary ellipsoids suitably defined. It won't change it. But the extreme, so what kinds of operators can you add? You can add division. You can add kth roots for fixed k. Doesn't change the class, okay? This is a very, very robust class. And in particular, it has complete problems. So, and the kind of canonical one is sort of computing an epsilon near approximation of a Nash equilibrium for a game with 3 or more players is both fixed P complete and fixed PA complete. So in other words, if you wanted to approximate it, then you should also be given epsilon. And it's complete in pretty much every sense possible. So computing a Nash equilibrium is complete for the class that I just described. So, I'm not going to describe games and equilibria, normal form games and equilibria and so forth. Sorry, I mean, it's not going to be the intense focus of the rest of the talk. So I hope most people in the audience are familiar with that. But we're going to now connect this to things that you might be more familiar with. Go ahead.
Instead of epsilon here, if you wanted the other version of approximation.
Yeah, we're going to get to that. Thanks for the question. So if we wanted almost approximation, that leads us to PPAD. And that's exactly why I'm sort of, and I'm going to explain the connections in detail.
And one more question. Suppose I wanted to exactly compute. Does that become...
Well, if you want to exactly compute an irrational value, what do you mean by that notion of exact?
Some bit of it, so significant bit.
That's, in particular, that's sharp p-hard. So we've shown, so one of the consequences of our results is that if you wanted to, if you're given the bit in binary and you want to compute the ith bit of a, let's say the Nash equilibrium of a 3-player game, that's a sharp p-hard problem. Okay? That's a consequence of that theorem that I just put up, but it's not obvious that it's a consequence. Okay. So, so what you might be familiar with, also in association with Nash equilibria, as I will elaborate shortly, is there's this class that was defined in the early 90s by Papadimitriou, PPAD. I'm not going to dwell on the original definition. The original definition, it's a purely combinatorial thing. You're given a succinct representation of a directed graph which has in degree bounded by at most 1 and out degree bounded by at most 1. And so by succinct representation, I mean you're given the adjacency matrix of the graph, but rather than being given it explicitly, you're given it by Boolean circuits, okay? And in such a succinct representation, you're also given a particular source node, in other words, a node that doesn't have any predecessors, and you're asked to find some other source or sink node, okay? And that's the complexity class PPAD that was defined by Papadimitriou in the early 90s. Now, before I get to sort of the famous results about by Daskalakis et al. And by Chen and Deng about PPAD, let me just connect it with what we've just seen. So the following problems are all p-time. The following are all p-time equivalent. The complexity class PPAD, which is everything that's polynomial time reducible to this search problem, is equivalent to what I'll call linear fixed p, which perhaps would have been better named piecewise linear fixed p. It's the fragment of fixed p where all I do is simply restrict my operators to plus and max, so I don't have times anymore. Okay? That and multiplication by rational constants. This is linear fixed p. This is equivalent, p-time equivalent to PPAD. Okay? And furthermore, this is also p-time equivalent to exact fixed point problems for something I'm not going to define completely formally. So polynomial piecewise linear functions. So think of this as a sort of a variation of linear fixed p that allows you a little bit more flexibility. I'm not going to describe it, but it's equivalent anyway. And it follows from a classic algorithm by Scarf, and this leads to your question over there.
I mean, your definition of PPAD is essentially the discrete version.
That's right.
So when you say linear fixed p, is this what you call fixed p A before?
Well, no. It turns out that when you restrict to this without multiplication, you always have a rational fixed point. And so essentially, basically, the rational fixed point will always exist, and I can reduce it to the exact problem. Okay? Okay?
The rational fixed point exists will be too large to write out?
No, it's always going to be polynomial size. Okay? So these are all interesting facts that follow as consequences of, in some sense, they also follow as consequences of some of what's embedded inside this proposition that where I'm gathering a lot of facts. But yeah, it's truth, okay? So another characterization of PPAD, which then follows, is there's a classic algorithm for fixed point computation in the almost sense, due to Scarf, going back to the 60s. And if you follow the details of that algorithm, it is precisely, basically, the kind of, it involves the kind of sort of Sperner lemma-based argument and path-following procedure, where what it does is it gives you an epsilon almost fixed point, right? In this case, not an epsilon near fixed point, an epsilon almost fixed point for a polynomially computable, polynomially continuous function. So whenever you've got the function for which you're trying to compute a fixed point is polynomially computable, and furthermore, polynomially continuous, by this I mean that you have a reasonable bound on the sort of modulus of continuity of the function. I'm not going to give the formal definition of this, but that's another characterization of PPAD. Let me mention something that I'm really, a recent result by Ruta Mehta that I'm quite enamored by, which is that she showed that actually you can take this linear fixed P and you can just restrict it to two variable inputs, right? So there are only, remember our general definition of fixed P, there's the number of variables is part of the input, right? What she's showing is that for linear fixed P, two variables suffice, okay? At the end of the talk, I might mention that for me, it's a very intriguing question whether it's conceivable that for all of fixed P, a bounded number of variables might suffice, but that's a whole different can of worms, and well, you can ask me more about it at the end of the talk, okay? I can see sort of, so I just saw Rahul's eyes like, they look like he was, yeah, okay. He was saying, are you bonkers? But yeah, I'll explain in what sense I mean, okay. Okay, so, okay, good. Now let me relate this to these celebrated results that you might have heard about. So by Scarf's algorithm, computing an epsilon Nash equilibrium. What's an epsilon Nash equilibrium? And let me call it an epsilon almost Nash equilibrium. What does it mean? This is the standard notion of an epsilon Nash equilibrium is a profile of mixed strategies in a game where no player can improve its own payoff by more than epsilon by unilaterally deviating from its own strategy. So it's almost a Nash equilibrium. It's not quite. Somebody can, in fact, deviate and potentially improve their payoff, but not by more than epsilon, okay? No single player can improve their own payoff by more than epsilon, okay? So by Scarf's algorithm, computing an epsilon Nash equilibrium is in PPAD. That follows from when you observe the kind of fixed point problems that Scarf's algorithm allows you to compute, in particular for Nash's functions, the functions whose fixed points give you the Nash equilibria. If you observe the details of that, you see that almost fixed points of those functions are indeed epsilon Nash equilibria, okay? And there's a more, even older algorithm by Lemke and Hausen for computing an exact Nash equilibrium for a two-player game. For two-player games, there always exist rational exact Nash equilibria whose encoding size is not too big, so the rational numbers are tame. And it follows from the Lemke-Hausen algorithm that computation is also in this complexity class PPAD. And there was this celebrated result by Daskalakis, Goldberg, and Papadimitriou, and by Chen and Deng. And Chen and Deng also did the exact version for two-player games that shows basically that sort of computing an epsilon Nash equilibrium for a three-player game is PPAD complete, and computing an exact rational Nash equilibrium for a two-player game is PPAD complete. But as I pointed out, unfortunately, Scarf's algorithm does not, in general, yield an epsilon near approximation of a fixed point. So in particular, these results don't tell us anything about if we wanted to actually approximate an actual fixed point of a Brauer function of the type that I was describing before, one that's described by, let's say, polynomial functions or more general algebraic functions. It doesn't tell us what we should do, okay?
We have hardness from this.
Absolutely, we have PPAD hardness from this, absolutely. Thanks for pointing that out, but we don't have an upper bound as such, okay? Okay, good. So let's talk about a different kind of hardness that one gets that makes it, let's put it this way, makes it very, very challenging to get the same kinds of complexity upper bounds. So PPAD is a total NP search problem class. It's a class of search problems that falls within, total NP search problems, okay? The hope of being able to near approximate a fixed point with the same kind of complexity is a bit shattered by considerations related to this Kousha LP problem. Those of you who were at the open problem session yesterday will have seen this, but I'll refresh your memory and for those who haven't been. So there's this Kousha LP problem, which just asks the following thing. You're given as input an arithmetic circuit, straight line program with plus, times, and minus gates, and with input 1, and you're supposed to decide whether the output value is positive or not. In general, you don't know how to do this in the obvious way in polynomial time, because if you just tried to evaluate the circuit, by repeated squaring, the numbers could blow up. So Kousha LP captures the power of what you can do in polynomial time in the unit cost arithmetic RAM model of computation. In a sense, it's complete for it under Turing reductions. We don't know, we have this upper bound for it, which is the 4th level of the counting hierarchy, but we don't know any better. And now let me relate this to the problems that we've been looking at. So Kousha LP, this exact decision problem, right? Decide whether the output of this arithmetic circuit is positive or not, is reducible to any non-trivial near approximation of a fixed point. Okay, so let's see. Any non-trivial near approximation of a Nash equilibrium is Kousha LP hard. What do we mean by this? More precisely, for every fixed epsilon greater than 0, Kousha LP is p-time reducible to the following problem. I give you a 3-player normal form game with the promise that it has a unique Nash equilibrium. The unique Nash equilibrium is fully mixed, by which it means that every pure strategy of every player is played with positive probability. Okay. So this, let X star be that unique Nash equilibrium. The probability that player 1 plays its pure strategy, let's call it pure strategy 1 or pure strategy alpha, that probability in the Nash equilibrium, the probability that player 1 plays its first strategy is either, I'm promising you, the probability is either less than epsilon or greater than 1 minus epsilon. Okay? And deciding which of these two is the case would allow you to solve Kousha LP. Okay? So any non-trivial approximation, it's an easy consequence of this statement that if you get any non-trivial approximation of an actual Nash equilibrium for a 3-player game, you will be able to solve Kousha LP. Okay? And okay, so what does this tell us? Where can we take this? Okay? So what makes a fixed point problem hard or easy? And you might say, okay, all right, forget about these funny complexity classes. Just tell me, is it NP hard or not, right? Okay? And the answer is that these kinds of problems are in general not NP hard and not likely to be NP hard because the existence of a solution is guaranteed by a fixed point problem. So there's no doubt that a solution exists, right? So these are total search problems. Now, PPAD hardness captures a combinatorial difficulty for computing or even almost approximating a fixed point. So that, and this is, in some sense, the insight of Christos was that you know, this combinatorially defined complexity class, PPAD, is a kind of a suitable way to kind of analyze the difficulty of fixed point problems from a combinatorial point of view. Okay?
So I don't understand the note. So how can you say they want general non-IP?
This is not a formal statement. This is saying that when you've got the existence of a solution, in particular, if you know that, let me give you a formal statement. Any total NP search problem, if you end up showing that it is NP hard, that will imply that NP is equal to co-NP. Okay? So now that's total NP search problems, whereas a real valued fixed P, in general, it's not a total NP search problem. But it turns out that you can get a similar consequence. What we show in the paper associated with these things is that if, let's say, a fixed P problem is NP hard, then it will imply, in particular, that the existential theory of reals is co-NP hard. Okay? And this is something that we don't, so in a sense, analogous to NP and co-NP are the existential theory of reals and universal theory of reals in the real-valued world, right? So you get funny consequences in that world. Nothing as dramatic, but these are things that there's been a lot of research on.
It's also surprising also the easiness of the existential theory of reals, right? So what are the hardness? You said that you get it.
What you get is that the existential theory of reals is co-NP hard, right? And there's, I'll get to my conjectures maybe, there's reasons to believe that that is not, okay? Okay. Right, so we've got PPAD hardness as a combinatorial difficulty of these problems. But it turns out that, but there can also be this additional numerical difficulty for near approximation. Not for necessarily for almost approximation, the combinatorial difficulty pretty much captures it. But for near approximation, you have this additional difficulty, that namely this pos SLP hardness. And the two are quite orthogonal in the sense that you encounter fixed point problems that have only one of these difficulties and not the other, or some combination of the two. And you even encounter things that have an intermediate difficulty. And so what I want to do is, in the rest of the talk, focus on a particular class of fixed point search problems, some of which are sort of this intermediate kind. But this is not a table that I can do full justice to, but it's meant to sort of give you some sense of the landscape that I want to sort of navigate a little bit for the rest of the talk. I'm not going to be able to do full justice to this, but what I'm trying to intuitively convey here is that there are sort of two orthogonal dimensions here, combinatorial difficulty and numerical difficulty. Along the combinatorial difficulty direction, at the extreme end, we have PPAD hardness for these kinds of fixed point problems. But there's also an intermediate difficulty, which I'll call parity game hardness. And parity games are, if you haven't encountered them before, so they are reducible. Solving parity games is in PPAD, but it's certainly not PPAD hard, okay? At least, say that again?
Certainly, yeah.
Yeah. So we don't know it to be. That's what I mean. We certainly don't know it to be PPAD hard. Okay. No. But there's more reasons than that, because it's both in PPAD and in PLS. There's 100 reasons to believe that it's not likely to be PPAD hard. Okay. So that's one direction. And then in the other direction, we have numerical difficulty, which, if you like, at the extreme end, we have pos SLP hardness. But it turns out that we also have some intermediate things in that direction, namely square root sum hardness and some other problems that I'm not going to dwell on. But in fact, in particular, polynomial identity testing, I kind of think of as sitting as the equality testing problem in the numerical difficulty direction. Okay? So it sits in here. So in particular, if you were able to get a polynomial time algorithm for fixed p, which would be a miracle, you would have also found a polynomial time algorithm for polynomial identity testing, okay? So approximating a fixed point would solve polynomial identity. Not that I'm suggesting that as an approach, but you know, it's kind of for those who are fixated on polynomial identity testing. That you know, okay. So okay. So so let me try to navigate this landscape by taking a very specific class of fixed point problems that are much more sort of tractable and end up yielding interesting algorithmic results. Okay. For the rest of this talk, I'm going to focus purely on monotone algebraically defined fixed point problems. And these turn out to have, firstly, they have many interesting applications, but they're also interesting algorithmically and from a computational complexity point of view. And so let me set this up. Okay. How many? Yeah. Okay. I'm doing okay on time, I think. Okay. So let me describe, so these are classic stochastic processes, multi-type branching processes. So what kind of stochastic process is this? So imagine a population of objects of distinct types. There could be red objects, blue objects, or green objects. And think of these as, let's say, cells, okay? There are red cells, blue cells, green cells. In each generation, a cell, which is, let's say, a red cell, can, with 1/3 probability, split up into 2 blue cells, a green cell, and a red cell. With 1/2 probability, it might split into a blue cell and a red cell. And with 1/6 probability, it might die, okay? So this, in a sense, this probability distribution on these multisets specifies the offspring distribution for a cell that is of red type. A blue cell with 1/4 probability might give rise to 2 red cells, and with 1/3 probability, it might die, okay? And a green cell with probability 1 might give rise to 1 blue cell and 2 red cells, okay? So, okay, so and in a very natural way, the stochastic process that this thing is defining is, in a sense, a process that generates a random labeled tree. We start at, let's say, a red object, and in one generation, if we happened to pick this rule, with 1/3 probability, we have generated these children. And then in the next generation, what might have happened is, from the 2 blue objects, we might have gone extinct. Right, we might have died. And from the red one, likewise, we might have died. But from this green one, without any choice, we would have had these offspring, right? And we might have these offspring subsequently. And it's indeed possible, in other words, it has positive probability that the entire tree might be finite, right? But it's also possible that the tree might, you know, with positive probability, never terminate, okay? So in other words, we may never go extinct, okay? So a fundamental question about these stochastic processes, in some sense, one of the first questions you ask, and this was already, the computational question associated with this was already addressed by Kolmogorov and Sebastianov in the 1940s, is what is the probability of eventual extinction starting with 1 red object, okay? So let's write down some equations for this, some fixed point equations for this. So let's associate a variable, x sub r, with the probability of eventual extinction starting with 1 red object, okay? So what is that probability? Well, consider this polynomial. What is this saying? I'm going to associate similar variables for the probability of extinction starting with each of the possible types, right? Now, with 1/6 probability, I'm going to go extinct in 1 generation. So that it's clear where this constant term comes from, right? But with 1/3 probability, I've generated these 4 objects as my children, and independently for each of those objects, I have to go extinct. So I have to effectively multiply the probabilities of all of those things going extinct, and that's where this monomial arises. And likewise, with 1/2 probability, I have to go extinct from one blue one and one red one, okay? Likewise, I'll write similar equations for blue types and for green types, okay? So lo and behold, we get nonlinear fixed point equations, in fact, polynomial fixed point equations, n equations in n variables, right? 3 equations in 3 variables. The fact is that, and this is not difficult to prove, but it requires a proof, but it's not difficult. The extinction probabilities are the least fixed point, the least non-negative solution of this fixed point equation, okay? What do I mean by least fixed point or least non-negative solution? I mean, it's a fixed point, and it is coordinate-wise less than or equal to any other fixed point, any other non-negative fixed point, okay? Now, the values happen to be irrational, and I'm approximating them here for this specific example, but it doesn't matter. Now, we're interested, obviously, in the general problem of computing these. So let me generalize this. So the polynomials on the right-hand side that we see here, these things are what I'll call probabilistic polynomials. So a probabilistic polynomial is just what you might think it is. The coefficients are non-negative, and they sum to 1. Okay, the coefficients of the monomials and the constant term are non-negative, and they sum to 1, okay? And a probabilistic polynomial system of equations is n equations of this kind, where each equation is a probabilistic polynomial, okay? So the right-hand sides are probabilistic polynomials, okay? So every multi-type branching process with n types corresponds to one of these probabilistic polynomial systems of equations, and vice versa, right? So in other words, if you start with one of these systems of equations, you can translate back to the branching process, which would have given rise to that for its extinction probabilities, okay? Okay, now let me generalize that, because we're going to later on refer to these as well, to the notion of a monotone polynomial system of equations. So monotone polynomial is just all of the coefficients are positive, okay? And again, a monotone polynomial system of equations is n equations in n variables, okay? So some basic facts about these. So for a probabilistic polynomial system, it's very easy to see that it maps the unit n cubed to itself, and it's obviously continuous because it's these are polynomials after all. So it defines a Brouwer map, but moreover, it also defines a monotone map on the unit n cubed. So a monotone map means that, just in case somebody is not familiar with, so let me just take some chalk. A monotone map f from the unit n cubed to itself is monotone if for all x comma y, x coordinate-wise less than or equal to y implies f of x coordinate-wise less than or equal to f of y. Okay? So just so in case somebody's not familiar with that. So these define monotone maps. And moreover, monotone polynomial systems of equations. Now we have to be a little bit careful here. So I'm attaching positive infinity, but basically it maps the non-negative orthant to itself. It's obvious that it does that. But for convenience, I'll attach positive infinity as well. And it's not difficult. If you just take the standard arithmetic when you add positive infinity to your, basically this defines a semi-ring, and there's a standard arithmetic on it. When you adopt that standard arithmetic, this defines a monotone map on the non-negative orthant with positive infinity attached. And here are some basic facts. A probabilistic polynomial system always has a least fixed point. This follows from Tarski's fixed point theorem. And so in other words, it always has a fixed point which is coordinate-wise less than or equal to any other fixed point. And the coordinates can, of course, be irrational. And a monotone polynomial system has a least fixed point. But now some coordinates might be infinity, But again, this is a consequence of Tarski's fixed point theorem because this thing defines a lattice, and by Tarski's theorem, it has a least fixed point. Let us call these monotone polynomial systems feasible if the least fixed point is non-negative. Okay? So, okay, good. So it turns out that, well, the least fixed point can be sort of attained, if you like, as the limit, as k goes to infinity, of iterating the polynomial system as a function starting from the 0 vector. Okay? So apply it to the 0 vector, then apply the result on the result, apply the polynomial on the result, and apply the polynomial on the result, and so on. And that will converge from below monotonically to the least fixed point. And these are, so this vector q star is indeed the, as we said before, this is the vector of extinction probabilities for branching processes, and more generally for monotone polynomial systems, this vector q star gives us what people call the partition function of the corresponding weighted context-free grammar. Okay? And this indeed has tangential connections to the kinds of partition functions that Leslie was talking about yesterday, but I don't want to take a detour to try to explain why people call this a partition function. Okay, go ahead.
So do you really know that it has a least fixed point, or do we also know that there is a total order between the fixed points? Like,
by Tarski's theorem, when you have a function that maps a lattice to itself, the fixed points of that function form a lattice themselves. So they form a non-empty lattice. Okay, so in other words, there's a certain structure there. And so it has a greatest fixed point and a least fixed point and so forth. Okay. Okay. So the question is, can we compute q star efficiently? And in particular, we're interested in being able to compute it or approximate these things in polynomial time. Okay. Now notice here that we're not interested in computing something that's almost fixed by these functions because that doesn't help us. We're actually interested in computing these probabilities, namely the probabilities given to us by the least fixed point. So we're sort of stuck. We need near approximation of fixed points, okay? Okay, so let me turn to kind of one of the standard workhorses of numerical methods that we're going to use to try to compute these things. Okay, so okay, so Newton's method. So I don't know what percent of the audience are, well versed in these things, but okay. So Newton's method is a standard method for attempting to find the roots or sort of solutions of differentiable systems of equations like that. Okay, we start at some guess, and then the iteration operation is as follows. So now this is the multivariate Newton's method. Some of you may be familiar with the univariate case, but it naturally generalizes to the multivariate setting, and it's basically this iteration. If we have the kth iteration and we want to obtain the kth plus first iterate from it, we take the old iterate, and this is the Jacobian matrix of partial derivatives evaluated at the previous iterate, then inverted. So this is the inverse of that matrix, assuming that that inverse exists. And this is just the function mapped on the previous iterate. Okay. Now, you might say, well, wait a second, is this iteration even in general defined? And indeed, it's not in general defined, but it's not always the case that this iteration might be defined. But for the monotone polynomial systems of equations that we're addressing, it turns out everything's going to work. Okay. So, in our setting, the Newton iteration looks like this. Basically, I'm just rewriting things because what we're going to need is we're going to need to compute a zero of px minus x, and then if we write it out explicitly, it's going to end up looking like that, where p prime x is just the Jacobian matrix of partial derivatives of the polynomials on the right-hand side of our monotone polynomial systems of equations, right? So again, the Jacobian matrix in the ijth coordinate has the derivative with respect to the jth variable of f sub I, okay? So, okay. Okay, so what's the connection? So it turns out that if you do some kind of pre-processing on your monotone polynomial system of equations, namely if you break it into strongly connected components based on the dependency graph of the variables, and if you then eliminate those variables that are going to end up being 0 in the least fixed point, which you can easily detect in polynomial time, then decomposed Newton's method converges monotonically to the least fixed point solution for both probabilistic polynomial systems of equations and for more generally for any feasible monotone polynomial system of equations. So we showed this back in 2005, but we did not give any upper bounds on the number of iterations that you might need to get within desired precision, okay? And we also proved that it is in fact posis LP hard to get any non-trivial approximation of the least fixed point solution for monotone polynomial systems that correspond to recursive Markov chains, which are a somewhat more general class of stochastic processes going beyond the branching processes that I showed you. And I'm going to show you an example of a recursive Markov chain now. So look at this. Think about these as representations of probabilistic procedural programs with recursion, okay? So you have some procedure A, and when you call that procedure with 3/4 probability, it will call itself recursively, and it can give you 2 return values. It can exit out of exit 1 or exit 2. Think of these as corresponding to 2 possible return values. And so it calls itself recursively, and then let's just suppose for this specific case that irrespective of what value that first call returned, it's going to call itself recursively again, and then depending on what value was returned, it will, with probability 1 in this case, exit, return 1, or with probability in this other case, with probability 1/3 return 1, or with probability 2/3 return 2, okay? So what is the probability starting at when you call this procedure, what's the probability that it will terminate, okay? What's the probability that it will terminate at exit 2, let's say? Okay? Do you want to write down some equations for that? Let's write down some equations. So let x2 denote the probability of terminating at exit 2, starting from the entry, okay? Well, we know that with 1/4 probability, we're going to go there directly, okay? And let's just write it out. With 1/4 probability, we're going to go there directly. Then what we have to do, with 3/4 probability, there's multiple ways we can do it. Either we have to exit at exit 2, and then exit at exit 2 again, and then, with 2/3 probability exit at 2. And if you take 3/4 times 2/3 there, what you're going to end up getting this term, okay? And you're going to end up getting this term if you do the other way of getting to that exit. And you're going to get this. Notice that this is a monotone polynomial system of equations, but it's not probabilistic because the coefficients sum to greater than 1. Indeed, it's not probabilistic, but nevertheless, the least fixed point gives us these termination probabilities for these things. And it turns out that for general recursive Markov chains, any non-trivial approximation of the least fixed point is posis LP hard, despite the fact that, so let me state it. Any non-trivial approximation of termination probabilities for these recursive Markov chains is posis LP hard. In other words, even deciding whether, given the promise that the termination probability is either 1 or less than epsilon, you can't decide which of the two is the case without solving posis LP. And on the other hand, epsilon approximation of these termination probabilities is in fixed P because we can actually reduce through some additional hacking of the function, we can make sure it has a unique Brouwer fixed point, which is as close as we want to the original least fixed point, and therefore approximating this, maybe it's in fixed P, and therefore it reduces to approximating a Nash equilibrium, etc. Okay?
Go ahead.
Okay, so 2 slides back you mentioned something like the least fixed point is the extinction probability.
That's right.
So why is not the case that any fixed point, what stops us? Is it easy to see that any fixed point won't be the extinction probability? It's like all ones is a fixed point.
Exactly. So you're saying what's the proof that it's the least fixed point as opposed to some other fixed point? And well, it's not a difficult proof. So you want me to prove it for you? I can give you the basic idea of the proof. Okay? So it turns out that if you look at this fact, let me go back a few slides. Look at this fact. It tells you that if you iterate starting from the 0 vector, the system of the polynomials on the right-hand side, if you iterate them starting from the 0 vector, you're going to converge monotonically from below to the least fixed point. Okay? What we can show is that this kth iterate starting from the 0 vector, it actually upper bounds the, so let's take it in the branching process setting. So, or let's take it in the recursive Markov chain setting. That's actually simpler. Pk starting from the 0 vector is an upper bound on the probability of terminating at, let's say, exit 2 within k steps. Okay? Now, take the limit as k goes to infinity, and that probability goes to and this value is always less than or equal to the least fixed point, and so you're sandwiched between those two, and in the limit you must be the same. Okay, that's the proof. Okay, so it's an easy proof. Okay, and as I said, in the branching process setting, this was a proof observed already by Kolmogorov and Sebastianov in the 1940s. Okay. But of course, it generalizes to these recursive Markov chains, which are richer. Okay. 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 So I've. Okay. So let me now go further. So we have this, but so what is Newton's worst case behavior? So in a pair of nice papers by Esparza, Kiefer, and Lutenberger, they studied Newton's method in more detail, and they gave some bad examples showing that already for probabilistic polynomial systems of equations, even when the termination probabilities are all 1, right? Starting from any, let's say, type in your multi-type branching process, the probability of termination is 1. You're almost surely going to terminate. Nevertheless, for those models that for the examples that they gave, they showed that exponentially many iterations of Newton's method are required even to get within just 1 bit of precision of in other words, to get above 1/2. Okay? So there are bad examples that show the worst case behavior of Newton already for probabilistic polynomial systems can be nasty. Okay? We're going to see how to circumvent this in a slide. Okay? So for strongly connected equations, they also gave exponential upper bounds for the number of iterations that would be required, but they gave no upper bounds in general. In a more recent paper with Alistair Stewart, we've actually shown tight matching exponential upper bounds that are essentially almost optimal in a number of important parameters of the problem, but I don't want to dwell on the worst case behavior for general monotone polynomial systems. I want to go back and focus on branching processes and the probabilistic polynomial systems of equations. And I want to state the theorem. So what does this theorem say? It says, given a probabilistic polynomial system of equations, we can compute a rational vector which is as close as desired to, so let's say within j bits of precision of the least fixed point, in polynomial time, both in the encoding size of the system of equations and in j, the number of bits of precision that we want. Okay? So, and we use Newton's method, and you should immediately be asking, how the heck do you do that? You just told me you've got exponential lower bounds on even just the number of iterations that are required. And so the magic is this. notice that this thing says the bad examples that the Esparza et al. Gave have the property that the least fixed point is the all one vector. And that turns out to be a case that we can detect and solve separately. And fortuitously, it also happens to be, in a sense, the only critical case which causes nasty problems. And so let me elaborate. So firstly, by old theorems about branching processes, it holds that for certain classes of strongly connected probabilistic polynomial systems, the least fixed point, or in other words, the vector of extinction probabilities is the all one vector precisely when the spectral radius of a certain matrix, namely the Jacobian matrix evaluated at the all one vector, which is also the moment matrix of the branching process, if that spectral radius is less than or equal to 1, then you terminate with probability 1, extinction happens with probability 1, and otherwise extinction happens with probability less than 1, strictly less than 1. Using this and a little bit of graph theoretic and sort of decomposition and so forth, you can give a polynomial time decision procedure for deciding whether any particular coordinate is exactly 1, and this is what we did back in 2005. And in fact, we used linear programming in our polynomial time procedure, and later on, Esparza et al. Observed that with a neat trick, they observed that you can actually do it with just solving linear systems of equations. And deciding whether the vector of extinction probabilities is, or a particular coordinate, let's say, is 0, is actually very easy to do in polynomial time. It just boils down to kind of an and/or graph analysis. It's very simple, okay? So you don't even need to look at the probabilities to determine which coordinates are 0, okay? Okay, good. So what's the algorithm? Given that now that we know how to remove the 1s and 0s, the algorithm is simply this. Find and remove those variables which in the least fixed point are 0 or 1. Remove them, plug in the associated values. You get a remnant probabilistic polynomial system of equations. On that resulting system of equations, run Newton's method, okay? Okay, good. So what does that buy us? Theorem. All you need is a linear number of iterations, 4 times the encoding size of the system of equations plus j iterations to get within j bits of precision, okay? Now notice that this we can do in the unit cost arithmetic model of computation in polynomial time in an obvious way, just do the iterations. If we wanted to deal with the Turing model, we have to do some rounding, okay? Good, let's do some rounding. So find